Okay, we have A, and we have, as I mentioned, a simple spring damper model. Therefore, we're having here a mass, M, and the mass is connected to a wall with a simple spring and a damper. Okay. And the spring has a constant C and the damper has a constant D. And on the right side there's acting a force with the value F. And we have here a general variable and we call that X. Okay, so in order now to derive a parameterized trajectory generator, we have to define the differential equation for this system. So the differential equation is simply the mass multiplied by the acceleration of the mass, and this is equal to all the forces. And if we are making, if we are cutting like this mass out and write it down here, then we can clearly define all forces, for example for the spring and for the damping force. So, and we have here then the spring force, here the damping force, and when we can define that, or both forces, we can define dependent on the constants of the spring and of the damper and the parameter X. So with that we get then Fc is equal to C multiplied by X, and Fd is equal to D multiplied by X dot. Okay, well, with these forces we can now complete the differential equation, and this is then simply F minus Fc minus Fd. And we can then rearrange this equation to the following: X dot dot plus dx dot plus Cx is equal to F. And this is our differential equation we will use in order to generate our parameterized trajectory generator. Okay, let's do that by simply writing here again the differential equation we just derived. And now let's transform this differential equation into a more convenient form. So our aim is to define a trajectory generator which has the following form: x dot dot is equal to something. So in order to do so, we are first dividing the whole equation by c, and then put the x on the other side. So what we got then is simply m divided by c multiplied by x dot dot plus d divided by c multiplied by x dot is equal to f divided by c minus x. What we can do now is redefine this term here. Yeah, we redefine this term and simply call the term g, and g defines then the target position for our trajectory generator. That means if we're using this system, what we will derive right now, then our system will be driven to this target position. So we can then write g minus x instead of f divided by c minus x. So in order to get this form here on top, we have to bring the rest on the other side, the rest like this, and we have to divide through this. So we can do that stepwise as well by first dividing, multiplying by c and dividing by d. That leads to m through d x dot dot plus x dot is equal to g minus x multiplied by c divided by d. Okay, now we can bring this term on the other side, which leads to m through d, m divided by d, x dot dot is equal to c divided by d multiplied by g minus x dot. Oh, this bracket is too much. Okay. So, and on the last step we can simply divide this term by this. So we get then in the end x dot dot is equal to d divided by m multiplied by c divided by d multiplied by g minus x dot, close the bracket. Okay, and we can, in order to have a real parameterized trajectory generator, we can simply redefine our parameter. We can simply call that beta, and this term alpha. And these are parameters which define, for example, kind of the stiffness and the damping of our parameterized trajectory generator. So we got then, in the end, the following term, x dot dot is equal to alpha multiplied by beta g minus x dot. And this is then, in the end, our trajectory generator. But this form, or this trajectory generator in this form, will simply leads us to our target position G. But in order to drive, for example, cycles or any possible trajectory, we have to add a forcing function in order to steer, for example, our vehicle or our model along a desired trajectory. So we have again this form, x dot dot is equal to alpha beta g minus x dot. And now we are adding simply a forcing function plus, and we call this forcing function f, and this forcing function is dependent on some weights w, and it's dependent on the time also. And this forcing function we have to learn by examples. So now we have the complete equation, and we could start to learn our weights in order to generate this required forcing function for a desired trajectory. But there is still a problem, since just imagine you have different trajectories collected. Like the aim was to make a sinusoid. Okay, you're going, you're trying to teach your robot to drive a sinusoid. So you're just simply drawing a sinusoid in a sketch, for example, like this. Okay, this is the time axis, and this is, for example, the variable x. Okay, and this would be the first sinusoid I have drawn. Okay, this is simply maybe here 10 seconds, here 0 seconds. So when I do this no more often, because I want to be sure that this is really a sinusoid, so I teach him, or I give him more sinusoids in order to learn the parameters really efficiently. So I would draw another sinusoid, and maybe it would look like this, and I have to draw another sinusoid, and maybe it drew like this, and so on and so forth, and another sinusoid. For example, it looks something like this. So what we have is that we can't be sure that the time or the period is always the same. So what we are doing is to define a starting point for every sinusoid and an end point, and then rearrange the time axis so that every of them starts with a starting point at 0 and with the end points at 1. And we call that parameter then that. Okay, so we're simply making that time independent. So we are normalizing our problem in order to use then also normalized basis functions, which we will see later. So in order to normalize now our problem, we have to do the following. We have again our equation, x dot dot is equal to alpha beta g minus x dot plus f dependent on the weighting parameters w, dependent of the d. We make it now, or we normalize now our function so that we got x dot dot is equal to tau multiplied by alpha beta g minus x dot through tau and plus f dependent on the weights, and now dependent on our normalized parameter z. Oh. Okay. So this is now our normalized trajectory generator, and now you're maybe asking which are these taus which I have introduced here. And these taus are a so-called temporal scaling. Okay, so just imagine you have now normalized all your, you have now normalized your desired trajectory on from 0 to 1. So, and this taus defines then the real time in which you really want to do your trajectory. Okay, so the bigger the taus, the faster the trajectory will be running through. Okay, So I will simply delete that. And now we are nearly done. Which is simply left is to define these forcing function. And this forcing function f dependent on the weighting parameters w is generated or is defined through normalized basis functions and is, as I mentioned, dependent on these weights, which we have then to learn by examples, basis functions. And this was now our task A from the first part of this exercise. And now we are going to part B of our exercise. And in part B, we really want to define this basis functions or this forcing functions and have a look into these normalized basis functions with which these forcing function is constructed. Okay.